Got it? I'll begin. Heavenly Father, we thank you for this day. We just thank you for this opportunity we have just to meet together and study your creation. We just pray that you again, Lord, be glorified in what we do. And we thank you for your many blessings to us this day, Lord. In your name I pray. Amen. All right, so something strange happened this morning. Like, I actually had a decent lecture in the first section. So I guess the odds are that this one's going to be bad. We'll see. But I like what I said, so I'm going to stick with it. Polar coordinates, right? We talked about polar coordinates before that unfortunate event yesterday. And, I don't know. I haven't graded it yet. Maybe there's a stack of hundreds waiting for me. Actually, I hope not, because it's out of 130. So, although many of you would be happy with 100, right? It's passing, I think. But, yeah. All right, I'm sorry. See, I'm already ruining this lecture with this talk of nonsense. So polar coordinates. Like, I told you last time that I was going to think of r as positive, right? But I also kind of warned you that we weren't going to stick with that long term here. So we need to talk about the possibility that r could be negative and how that works. That's the first order of business here. Just to give you an overview of where we're going, we're covering today basically sections, I think, 10.2 and 10.3. What I'm doing is I'm combining these sections. What we're going to do is we're going to talk about how to graph polar equations, and then after each example, as appropriate, we're going to find an associated area. All right? Because the problem of finding polar areas and the problem of polar graphing, these are very much connected tasks. All right, but first things first, we need to understand what it means to have negative radius. So technically, r could be plus or minus the square root of x squared plus y squared. That's what's understood in this chapter that we're studying. And both those choices, it's still the case that x is equal to r cosine theta and y is equal to r sine theta. However, not for the same theta, all right? Like, let me explain. So this particular point, 1, 1, all right? You could either understand it in terms of the standard polar coordinates that I talked about last time, which is my default, like r1 equals to the square root of 2 and theta 1 is equal to pi over 4, all right? You could do that. But you could also be weird. You could say this point is really r is equal to minus the square root of 2 and this angle, theta pi over 4 plus pi, 5 pi over 4. So you could say that this point is actually 5 pi over 4 at radius minus 1. So negative radius flips you over the origin to the other side. Let me show you how that works. In terms of the formula, r2 cosine theta 2 minus the square root of 2, cosine of 5 pi over 4, well, that's minus root 2 times minus 1 over root 2, which gives you back 1. As you can see, it's legit. I mean, it does give you back the same x, right? X is 1 with either choice of polar coordinates. But the danger here, of course, and the annoyance, is that now there's not a single choice of polar coordinates, right? Any point could be given two different polar coordinate pairs, right? Either with a positive radius or with a negative radius, but with different angles, right? Now, okay, you're like, well, we already had the angle degeneracy, so it's not so much worse, right? You already had the problem that you're like, well, you said it was square root of 2 at pi over 4, let's say 45 degrees, but you could just as well say 45 degrees plus 360, or or pi over 4 plus 2 pi, or plus 4 pi, or plus 8 pi, or plus any even integer multiple of pi, right? That's geometrically the same angle as pi over 4, right? So we also have that degeneracy to deal with. So I mean, what I'm trying to tell you is, if you narrow down the subject of a criminal investigation to a particular polar coordinate, you've still got a lot of people to question. All right, that's what I'm trying to say. They're not unique. Sorry, and reaching out to the criminal justice segment of my class. How many criminal justice majors here are taking Calculus 2? This is why you should not argue calculus with state troopers when they stop you. No, I mean, I know a straight trooper at my church. He's a nice guy, but he says the thing most people say about math. It's useless? How dare you? Get out! No. Actually, that's fine with me. If it's useless but beautiful, I'll take it. But I don't really believe. I don't think actually that. I mean, math is a language, all right.
Yeah.
So it's going to be useful. Whether or not we know the use at the moment is somewhat irrelevant. If adding more words gives us deeper understanding to the syntax, then it's worthwhile. Anyway, I digress. So here's a general derivation. If you change theta to theta plus pi, all right, and you swap out your positive r for minus r, right? Just think of this r as being the plus r, right? Think of this r as being, for a moment's discussion, think about this r being the actual square root of x squared plus y squared, all right? If you did that, and if you think about the theta being the standard standard angle for a second, all right? Standard angle is measured counterclockwise from the positive x-axis. It's true. All right, anyway, so if you do that, then adding angles formula gets you to here, but sine of pi is 0, and you get minus times 1 times minus 1, gets you back to r cosine theta. So you can see that like it's not a quirk of my example that it worked out to the same thing, right? It's a general feature of this. If you trade theta for theta plus pi and you swap out r for minus r, you're still at the same point. Same x value, right? And likewise, you see what happens with the minus r and the sine theta plus pi. Well, adding angles formula pops out a sine theta cosine pi, and again, this is 0 because sine of pi is 0. And so there you're back, y is equal to r sine theta. So it really, you have these competing descriptions for a given Cartesian point, right? You can either use positive radius or negative radius, and you have your choice of standard angle or the non-standard plus pi angle, all right? So my next example confused the earlier section a little bit because I switched gears here a little bit. This whole discussion, I'm fixing a particular point, really, and I'm like just analyzing different polar coordinates for that same point, all right? This point down here, for what it's worth, what are the polar coordinates of this? R equals the square root of 2, theta is what? Standard angle is what? No. Pi plus 225 I would take, but I was looking for, no, yeah, 5 pi over 4, right? I should use radians. It is calculus after all. But I do think in degrees, I'll admit it. So that is this point, all right? In the standard polar coordinates, right? So over here, just to continue this discussion, to try to let this negative radius thing sink in, one more example. If I have radius 3 and pi over 3, like up here, right? On the other hand, I could describe this particular point as also minus 3 and angle pi over 3 plus pi. I mean, I think that the description in pink is weird, right? Yeah. And but there it is. On the other hand, this point down here, Q, well, this has theta equals to pi over 3, but r is equal to minus 3. See how that works? So pi over 3 is up here, but if I have negative radius, it flips it over. All right, you're like, so why don't we, if we can describe everything geometrically, right, with just positive radius, why don't we just stick with that? All right, I'm right there with you. We could do that. But then the graphing of polar equations would be complicated by like using absolute values and things. And it would probably, I mean, it would make it less natural. If you think about the examples which follow past this point, they're just much easier if we allow for negative radius for the follow. Well, you'll appreciate it as we go on. But my first example, graph r equals sine theta in the xy plane. All right. So there's two different graphs you can think about, right? The first is just the r theta graph. That's not the Cartesian plane, right? That's the r theta plane. And in that, we already know how to graph sine theta, right? It's a sine function, like this, right? The point is, this sine function does take negative values, right? And we're stuck with those. We have to interpret those, and that's what we're going to do. Let me get rid of the mysterious fan stuff in here. Not relevant to us yet. Sorry, I was trying to erase the irrelevant bits before we started, and I missed this one. Let me forget this here. So I started with 1, 2, 3, 4, but then I decided I need some points between, so I made 1.5 and 2.5 and such. Okay, so the point is, if you follow the sine graph, right? If I start here, 0.1, that's at the origin, right? Then 1.5 was what? That would be like pi over 4, right? Which is like 45 degrees, and it's about 1 over root 2. Now this may or may not be quite, I mean, it's the best I can do without having graph paper up here, right? And a compass and so forth, whatever. So that's that 0.1, 0.5. 2, well, that's radius 1 at pi over 2, right? Or 90 degrees, if you like to think that way. That gives me this point up here, right? I get to 2.5. I am now over to another 45 degrees further, right? I'm at, like, what is that? 3 pi over 4. And my radius is like 1 over root 2 again. That's this point, right? So I've gone from here, up to here, over to here, down to here. And then I get to 0.3. 0.3, I have radius equal to 0. What's my theta? Pi, right? So, but radius equal to 0, what are the angles at radius equal to 0? Everything. Theta is not defined at 0. So I mean, like, theta equals to anything you want at 0. All right. So if our polar equation, if our polar graph, right, the r theta graph, if it comes back to 0, that's the origin in the corresponding Cartesian graph. Them's the rules. And it goes back, of course, to these equations, right? If you put r equals to 0, you got x equal to 0, and you got y equal to 0. And that's all, I mean, that's the origin, right? It's inescapable. Doesn't matter what theta is. Get to 0.4. Well, 0.4 is where? That's at, what, 3 pi over 2, right? This is at 3 pi over 2 in the sine function. And r equals to minus 1. So 3 pi over 2 is down here, right? But we've got minus 1 radius, so it comes back up there. In other words, the 0.4 and the 0.2, those are the same, those map to the same point in the xy plane. And then we continue. When we get back to 0 at 5, we're back to the origin again. And so and then we're just going to keep going, retracing these steps again and again and again. And I think from what I've done so far, I mean, there's not, if I threw in more points, you'd see more clearly what it is. But at the moment, I can't really tell if it's a circle or if it's like something else. Definitely, I feel like it's a circle, but I haven't really proved that yet, all right? I have a suspicion that it's a circle, though. So, this kind of graphing, all right, is useful to figure out, like, heuristically what the graph looks like, right? If you do it carefully, you can at least find out, is it like a closed region? Is there a loop in it? Is it open? What's its general shape, right? To be more explicit, this particular problem, though, allows an algebraic solution as well, right? So if you start out with r is equal to sine theta, what you can do is you can also solve this problem algebraically. Here's how. Multiply by r. Why do I do that? I do that because I know that r sine theta is y. So I'm trying to convert this to Cartesian equation. What's the Cartesian equation? Right, it's an equation just involving x and y. The theta and the r dependence has been traded for x and y. All right? Why is it a Cartesian equation? It's in honor of René Descartes. Or as a person in my Rise of Modern Science class called him Descartes. Although I was talking to my friend at the time, so I missed it, sadly. Oh well. We had lots of fun arguments with engineers. I was one of 4 physics majors in there. Let's see here. Y squared to y. So there, now it's a Cartesian equation. So if you're just interested in converting to a Cartesian equation, we're done. But we want more. We also want to understand which Cartesian equation this is, right? So put all the stuff on one side, complete the square, and you'll have it. All right, so if you complete the square, you got x squared plus quantity y minus a half squared equals to 1/2 squared. And it's manifestly clear from the last formula, right? This one I'm about to put a box around. This makes it manifestly clear that this is a circle of radius 1/2 centered where? I heard 1/2, but you meant 0 1/2, right? Okay. So in other words, my graph is not very good because I should have made a circle, right? And its center is right in there, all right? It's a circle of radius 1/2 centered at 0 1/2. Now, as is often the case, algebra gave us precise data, whereas graphing only gave us qualitative data, right? Graphing is a qualitative tool, unless you use a computer, in which case it's still a qualitative tool. But it's a better qualitative tool on a computer. Yes?
When you substituted for r, shouldn't it be square root of x squared plus y squared? Or did I miss something like that?
R squared, though. R squared is x squared plus y squared. Yeah. It's interesting. As I think about these problems, I almost never find myself writing the square root of x squared plus y squared anywhere, except here. Did I get it? Yeah. I wasn't looking. That's funny. Was the video on it? Yeah. All right. All right, you made my day. I feel like I got to throw this marker and see if I can make it right now. I just feel like that was a good marker, though. I shouldn't throw that out. You never know when there's like a half-eaten yogurt in the can. I mean, fortunately, we don't have chewing tobacco here much, so there's that. But all right, so the application to areas that I had promised. All right, so that's our first example. We'll do more. How do you calculate the area bounded by a polar graph? So here's sort of the generic problem. Suppose that you have an area that looks like this. So what you're looking at is some kind of sector with the outer radius being variable, but it's a function of theta, all right? So the outer radius is like a function of theta. You've got some starting angle, you've got some ending angle, and you'd like to know what's the area of this kind of weird-looking sector. I mean, it could, you see what I'm saying? The idea of it, the setup? I hope. Now, so like, for example, r of theta for this example is just sine theta. the r of theta, the function of theta, is just sine theta for our example we just did. Okay. So how do you calculate the area of something like this? Well, what you can do is think about chopping it up into a bunch of little infinitesimal sectors, right? What's the area of a little sector like this? If it has angle subtended d theta and the radius is theta, well, the little bit of area from this one, dA, it's just 1/2 r squared d theta. You know that? To find the area of a sector, you do 1/2 the radius squared times the change in angle. If you don't believe me, all that formula says is that the area subtended by a sector with radius r is proportional to the angle subtended, such that when you go all the way around to 2 pi, you get pi r squared. Right? If you put d theta equal to 2 pi, you can see why that half is absolutely necessary, right? Because of course, when we go all the way around, we should get pi r squared, right? So that half is a necessary scale factor to appropriately apportion the area based on the d theta subtended. And then, so to find the whole area, as the radius is varying, you just add them up. You take the continuous sum. This is integration, right? Of course, we could formalize this with a careful Riemann sum and take the limit and gain little from doing that, I think, personally. But there it is. So this is the area of a polar sector. All you do is integrate 1/2 the radius squared over the appropriate range of theta. Assuming that the polar area you're looking at has that simple format, right? In other words, if you draw a ray from the origin, you have to stay inside the area at each point in your region. That's what I was drawing over here, right? So if you pick the origin, right, and you draw little lines out to the edge, you see there's a clear area which is bounded here, right? See these sectors? There's nothing outside the r equals sine theta graph. So I can calculate the area bounded by this radius function in that way. Now, don't look. It's too late. You probably already saw it. So what should I integrate from? See, we'll never know. Man. Do you see why that is, though? I mean, I think it takes a little faith the person to first say that, because you're like, it doesn't look like it's really, especially in my picture, it doesn't look like it's really getting to pi, right, or to 0, because but you see it does. The tangent to the bottom, right, it's at 0 on the one side and at pi on the other. And so the angle's sweeping from 0 all the way around to pi. So, but I will freely admit that is not always obvious to everybody. But it's true. 0 to pi. And then you integrate. So 1/2 sine squared, right? Half angle, that's a quarter. 1 minus cosine 2 theta. Integrate that thing. You got yourself a theta over 4. And minus 1/8 sine 2 theta. Evaluate that thing from 0 to pi. Sine of any integer multiple of pi is 0, so that's 0. And this just gives us back pi over 4, which is also known as pi times 1/2 quantity squared, which is, of course, really not surprising, given that this is a circle with radius a half, so its area is pi times 1/2 squared, right? So the reason I'm doing this, of course, is not to show you the best way to calculate this area. I am merely trying to illustrate how we calculate area based on polar formulation of area calculation, all right? Does that make sense? Yes?
Doesn't it have to be resting on the origin?
For our setup, yes, because we're integrating sectors, which are based on the sector going all the way to the origin. Now, since you asked the question, you're right. We could consider more general things, right? You could consider something like something that had some sort of shape like this, right? Where you had an inner radius and an outer radius, right? Like, let's say r is equal to, say, I don't know, g of theta out here, and r is equal to f of theta. I'm not following the book. If the book has some privileged notation for one being f and one being g, sorry, tell you what, why don't I just do r in and r out? The book definitely hasn't used those, so there we go. So r out is some function of theta, r in is some function of theta, all right? Then, to calculate the area of something like that, same song and dance, you just divide it up into like little wedges, right? Little sectors, but I'm not doing it. It is, you know, like this. But the dA would then be 1/2 r out squared times d theta, right? That would be the area of, let's say, the whole thing, right? And then I have to subtract the area that's missing, which is the r in the area of, I'll graph it here. I have to subtract this area, right, to be fair. So minus 1/2 r in squared d theta. So in other words, I get dA is 1/2 r out squared minus r in squared d theta, and the area, the total area of such a region is the integral from theta 1 to theta 2 of 1/2 r out squared minus r in squared. Yeah. Although I was planning for those examples tomorrow. But that's fine. It's good. Natural question. If we came to it, we came to it. Now, of course, yeah.
So that's basically just like calculating the area of any that we've done in the past, but instead of from like x value is angular.
Right. It's a way to set up the calculation of an area if the area has some kind of polar presentation. If we have some natural polar characterization of the area, r is a function of theta, and it happens to be an area which is bounded, like this circle. Or it could be weirder stuff, like check this out. Another example. This is a wrong example, all right? But it's an example I show people just to illustrate what not to do. So let's suppose you're going from the point 0, 1 to 1, 0. I want to calculate this area here. So you see what I can do? I can of course, from the origin out to here, there's definitely just this outer radius, right? What is the outer radius in this case, though? I mean, it's pretty clear. 0 is less than or equal to theta is less than or equal to pi over 2. That's easy to see here, right? Okay. For this region that I'm trying to, let me hatch it again here. So what's the formula for the radius there? Well, here it's not obvious, right? Here you actually have to do some work to discover it. In Cartesian, this is y is equal to what? Y-intercept of 1, slope minus 1. So y minus 1 minus x is the Cartesian equation. Converting that to polars gives me r sine theta is equal to 1 minus r cosine theta. So what that gives me is r times sine theta plus cosine theta is equal to 1. Hence, r is equal to 1 over sine theta plus cosine theta. And so the area of this region is 1/2 the integral from 0 to pi over 2 r squared. What's r squared here, though? It's 1 over sine theta plus cosine theta quantity squared d theta. And so you just got to do that integral. In fact, it is 1/2, right? Yes. You're really good at integration. Of course, Travis knows that this is a triangle, with base 1 and height 1, so its area is 1/2 base times height. I hope you know that as well. I hope you knew that. I hope you've known that for a long, long time. I really do. But yeah, so the actual calculation of that integral is fun. But this is obviously the wrong way to calculate this area. Why? Because this is not a polar thing, right? This is a Cartesian thing, and it belongs to the world of Cartesian calculations, right? You shouldn't calculate the area of a triangle using polar coordinates. It's dumb. Okay. But this example is not dumb because it illustrates a non-trivial r. That's the point of this example. R can be a function of theta in an interesting way for uninteresting things. And if I had something like, I don't know, this, and then like that, maybe that's not, let me try again. I don't know, it could be like one of these deals. Whoop, whoop, something like that. Maybe this is r out as a function of theta. Well, then you'd need this r in would be this thing I just found, right? And then you couldn't avoid the integration. You'd actually have to face the music and do it. But, for a weird shape like that, you'd tolerate it. Okay. Let us do another graphing example. Yep.
Would you just subtract 1/2 from the area integrated?
Yeah, you could. Oh, that's smart. Yeah, I like that. Let's see here. Let me rain on your parade. There. I don't even know. I'd have to really think about it. Okay, let's get back to examples that we should talk about. But yeah, you're right. You can get away with that. So I don't know why I erased this. I'm going to try to talk through it step by step with you guys. I gave up on my numbering and started color coding at this point. So, well, first of all, here my first example is easier. Here, let your brain relax for 10 seconds. What is the Cartesian graph of r squared plus r equal to 0? Okay, factor out r. You have r times r plus 1. So either r is equal to 0 or r is equal to minus 1. Think about what r equals to minus 1 is, though. It's just, if you let theta range over its values, right, it's still a circle of radius 1. Just with a weirdly described radius, right? But it's still the collection of points as theta ranges over all values is the unit circle. So what you have is the origin and the unit circle. That's it. That's the graph. No need for, this stuff, right? This stuff, I should say. So here's a more interesting example, r cosine 2 theta. So the approach here again is to carefully graph the r theta graph, all right? The polar graph, create the polar graph, and use the polar graph to then create the Cartesian graph. And so I just think about it step by step. I found it useful to partition my thinking into looking at one petal at a time. Let me explain. So I start out with the blue. You see, r is equal to 0 at where? When this is minus pi over 2, and when this is what? Pi over 2, right? So that's from minus pi over 4 to pi over 4, because I have to multiply by 2, all right? So basically what's happening, as you range your angle from minus pi over 4 to pi over 4, r is positive, right? So I can think directly about standard angle in the usual sense. And what I'm doing is I'm ranging from the origin out to radius 1, back to radius 0 again as I trace through angles minus pi over 4 to pi over 4. So what I've done is I've drawn some asymptotes. These asymptotes are at plus or minus pi over 4, right? So the graph that corresponds to this part of the polar graph is stuck between these rays, plus or minus pi over 4, right? And what happens is it starts at 0, right, at minus pi over 4, let's say, traces out here to 1 at theta equal to 0, and then it comes back to the origin. All right, and that completes the story of the blue part of the polar graph. Now I'm to the red part. And so if you look at the red part of the graph here, we're going between pi over 4 and 3 pi over 4, right? But pi over 4 and 3 pi over 4 is up here, of course, right? But what's the deal? R is negative here, right? So it flips over. So it's down here because R is negative. The pi over 4 flips to 5 pi over 4. The 3 pi over 4 flips to minus pi over 4 geometrically because the radius is negative in the red part. But you can see the graph continues if you just follow it, right? We had this blue, it goes like this. Whoop. Like that, right? It just continues on. And again, you go down to radius 1. Well, in fact, this is radius minus 1 at pi over 2, right? Pi over 2 is up here. Radius minus 1 at pi over 2 is that point. So we're using this negative radius stuff I talked about at the start of class to make these graphs, all right? Then what's next? The green. Green goes from 3 pi over 4 to 5 pi over 4. The radius is positive, so I can think about that directly in terms of the actual geometric angles, standard angles, 3 pi over 4 to 5 pi over 4. That's 3 pi over 4 to 5 pi over 4, right? So if you were following on the red graph, we got to here, and we just keep going through, and we loop, right? And then that gets us to this point. And then, let's see, the pink graph goes from 5 pi over 4 to 7 pi over 4. However, which would be what? That would be down here, right? But the radius is negative. So again, we flip up. We reflect the 5 pi over 4 to pi over 4. We reflect the minus pi over 4, or 7 pi over 4, the 3 pi over 4 up here. And that gives us this pink petal. You could argue by symmetry, right? There's no difference. There can't be a difference between these petals, right? So once you've done one, by symmetry, the rest have to follow. That would require, that's something you should say once you have a little bit more experience. I don't think that's a reasonable thing for you to say entering this study. But once you've worked a bunch of examples, you'll see what I'm talking about. And the symmetry I'm talking about maybe will join your intuition, right? Yes, question? No? So to reiterate, you can look at this like this. Wee. Oh, I almost lost. I almost got off track there. Let me try again. Wee. That's not. I think that's it. I think that's all I got. But yeah. All right. Do I have anything else? Find the area. Well, one more thing before I find the area. I'll do the area. Let me do the area. So the area of the blue petal, right, would be integrate from minus pi over 4 to pi over 4. 1/2 cosine squared 2 theta, because cosine 2 theta is the r, right? And there's clearly, if you look at the blue petal, it goes from the origin out to the cosine 2 theta curve, right? There's no inner radius here. It's just that, right? And so I do this integral, but I'm lazy. I exploit the symmetry. Of course, that would be twice the integral from 0 to pi over 4, right? I mean, why not? So that's why the half gone. And then I do the half angle or double angle formula, whatever floats your boat. 1/2, 1 plus sine 4 theta. Integrate that thing. You got yourself a theta over 2 and a minus 1/8 cosine 4 theta. When you plug in pi over 4, you get pi over 8 from the theta over 2, and you get a minus 1/8 cosine pi from the upper bound, and you get plus a 1/8 cosine of 0 from the lower bound. And so in total, we have 1/8 times pi plus 2, and that's the area of that petal. If you wanted to find the area of the flower, multiply by 4, right? That make sense? I don't know. You can disagree or agree, whatever. Now, this generalizes, right? Let me just bump it up a notch here. What if you thought about r is equal to a cosine of n theta? If you followed this example carefully, I'll let you guys catch up first. You guys are still working on my area. Calculation. You guys with me? Every once in a while I find out people are like 3 or 4 minutes behind where I'm talking. It's disturbing. All right, this means Mackenzie's still writing. I should like just stop talking and like hit a stopwatch and see like how far you guys are behind. It'd be fun. Anyway, I'm being silly. That goes without saying. So if you think about this, for n being a whole number, all right? What are we doing? Basically, how do you get a petal? What does the 2 theta have to range through? We're going between zeros of cosine, right? How far apart are zeros of cosine for the argument? Pi, right? Every pi, you go from 0 to 0. You swing to 1, and then you swing to minus 1, and then you swing to 1, you swing to minus 1, but it's pi. So if you think about this, if we look at pi, right, is equal to n times the change in theta, where this is the change in theta for a petal, single petal, if that makes sense to you. That should be the characteristic of the n-fold graph. And so if you ask how many petals there are in that, what you should do then, of course, is say, well, 2 pi divided by delta theta, right? That should give me the number of petals, right? If the change in angle that's the angle for one petal, if I take 2 pi and divide by change in theta, that gives me the number of petals, assuming that makes sense. So what is that? 2 pi divided by what? Pi over n, right? Solving this for n, right? Change in theta is pi over n. And that gives you what? (2n), right? So the number of petals is 2n. N equals 2, 4 petals. If you looked at the graph of cosine of 3 theta, you'd get 6 petals. Cosine of 4 theta, 8 petals. Cosine of 5 theta, 10 petals. If you look at graphs of like r is equal to something like a sine of n theta, what do you think happens? I don't know. Let's find out. So what we're doing, of course, is important. You need to understand what we're doing too, right? But you shouldn't stop by doing things by hand. I mean, you have to do things by hand to start with to understand what's going on, right? But after you start to gain traction conceptually, you should start using technology to aid your understanding, right? The proper use of, for example, of graphing calculators in college algebra is some sort of interplay between graphing and actually using graphing calculators to explore examples. But nobody does it this way, right? You just try to think with the graphing calculator. You should use the graphing calculator to explore. You should use your mind to think, if that makes sense. So we should use technology to explore, I think, that's what I'm trying to get across here. So of course, you can check your answers here. What did I do? Oh, sorry. See, I knew her better. I could insult her somehow. Fortunately, I don't. Oh well. You can ask.
Pretty much rhetorical, but I have a very expensive graphic calculator.
No.
But I do not know how to use the graph.
Oh.
Is that bad?
Have an expensive graphing calculator, don't know how to use it. I don't know.
I only know how to use it for basic stuff.
Oh, basic stuff? I think maybe you should. Seems to me like you need to sell it. Take that money and go watch like 3 movies. I would have said 30 movies a couple months ago. Maybe you can go jump on a trampoline soon or something. I don't know. Stupid trampoline. What movie theater back? Sorry, I digress. I'm not sure how to solve your problem. I would say this, and my brother made this point to me, and as soon as he made it, it's been a point I've been making because it's just logical. No one should buy graphing calculators anymore because you have smartphones, and the Wolfram Alpha app is $2, and it will beat down graphing calculators with a vengeance, right? Why would you buy a TI whatever with a... You're not allowed to use the TI 85 on the test either, though, so...
You can in statistics.
Oh, in statistics you can?
There might be other engineering.
I feel you. The part of the reason I got an A in quantum mechanics was that I had a TI 89. Yeah. Integral sine cubed. Whatever. 3/8. Now, the thing is I could actually do those integrals, but it saved me time. So that's the thing is the T89 was a reliable tool in my hands because I knew calculus. If you don't know calculus, well, you know, it's kind of like wiring a house without knowing the difference between ground and other stuff. Yeah, you might get electrocuted. It might work. I don't know. Oh, I'm sorry. I seem to have talked about nothing, and now we're almost out of time. Look, so this is Desmos.com, a free graphing calculator. This is kind of fun. What you're looking at here is actually different cases for the ellipse. Woo-hoo. These are rotated ellipses. I think the formula is a little bit more general than the one we had. But you can see different eccentricities, circles, hyperbolas, parabolas. Now, let's see here. Let's change this up a little bit, though. Oh. Let's say, what do we want to do? Sine of do AT? How do I do, what's theta in here? I don't know. Is there a theta button? Is what? You guys are smart. All right. Check it out, yo. Yeah, it is a spiral. All right, so like there's a equals to 3, right? But if you go non-integer, I want it to slower still. Slower, come on, man. See if I can make it bigger. Let's see here. Oh, come on, I want to zoom in. What's that? Oh, yeah, thank you. All right, let's see if I can't. Oh, come on. I want to... Let's say between... let's say between 1 and 3. And we'll do 1,000 steps. Okay, so the n equals 1 was a circle, right? And when we finally get to 3, what do we have? Oh, we'll be way over time, won't we? So as you can see, like, okay, so here's the thing, is if you actually have, basically it's this, if you have a rational coefficient, if the n is a rational number, it will be a closed cycle. If you actually have an irrational number, it doesn't ever come back where it started. It just keeps looping like a spiral graph. Whee! Oh, and as you can see, when we hit 3, we had 3 petals, right? So apparently sine of n theta is actually just n petals. What's that? 2? Oh, apparently I'm wrong. Let's see here, 3. I don't know, that's interesting, isn't it? So for even, we get double. For odd, just exactly what it is. Why is that? Interesting. Yeah, we'll have to sort through that, huh? Oh, finally, one other thing. Weird stuff happens if you do like 1 plus this. Totally new stuff. Or a plus this, right? Yeah, I'm sorry, I know you guys got to go. This gives us the limicons and the lemniscates and the... It's all in your book. It's got names. Sorry, I shut up. Happy convo to you all.